Good morning, everyone. Welcome to our session on design examples of slopes and soil structures. I'm delighted to see you all here today. My name is Natalia, and I'll be your moderator today. Let me start with a quick overview of the program. We'll have a short, not so short, introduction, and then 3 examples from TGB1 and TGB2. Just before lunch, we'll have, I hope, 15 minutes for discussion. So I would encourage everyone to prepare the questions for the speakers in advance, and also to our speakers and to myself especially, to be mindful of time, because we want to ensure to have this discussion session, as this is the heart of the seminar. Let me start with the introduction on slopes and soil-made structures. Regarding my background and why am I at all here, I'm a geotechnical designer. I work in EC7 Titan in Poland. I've been involved in works regarding Eurocode 7 since 2018 already, as somebody reminded me yesterday. I worked in TGB2, and I also had the privilege to lead a subgroup working on soil nails and rock bolts. So let's dive in. I start with the slopes. It's not a new content in Eurocode 7, as you are well aware. However, there are some improvements in the second generation, and I marked here some sub-clauses which are worth of special attention, and I will focus on them today. However, I would like to remind you that 3 weeks ago there was a very nice, interesting webinar organized by NEN, and Witold Bogusz has a very detailed, great presentation on this topic during this webinar. So I would encourage you to visit the NEN website to check all this detailed information. But about some basic assumptions, clause 4 applies to overall stability, local stability, and displacement of cuttings and embankments. It covers dams and reliefs, but under specific conditions that verification of water retention is excluded, and we also should remember that in consequence class 3 and 4 we may need some additional provisions. Obviously, Eurocode 7 Part 3, including slope clause, has to be used in conjunction with other Eurocodes, and especially important in the context of slopes, the execution standard for the earthworks. What's important, clause 4 applies to overall stability not only of the slopes, but basically all other geotechnical structures covered in Eurocode 7 Part 3. So it makes it one of the more important clauses. When we begin design process, we usually start from the ground investigation. Clause 4 gives some guidance regarding the extent of the field investigation with the values of depth of the field investigation. But what's important, and I would like simply to remind it, in case of more complex structures, we shall check those values for every individual, let's say, of these substructures. But at the very end, we shall have in mind that what we have to cover in field investigation is not this number, but is the zone of the influence. So this is the crucial thing, and there was a great session yesterday by Håkan on this aspect. When it comes to the verification methods, all defined in Eurocode 7 Part 1 are allowed for slopes. Then regarding the geotechnical analysis, the stability of slopes shall be verified either or with very popular limit equilibrium methods or numerical models, and there is a special chapter on this aspect in Eurocode 7 Part 1, or with limit analysis. Eurocode 7 does not give any specific guidance which calculation model should be used for our case. However, in Annex A, there are some comments, information regarding calculation models for soil and fill, and also for stability of rock mass, which may be helpful in those decisions. There are also some additional considerations, which I think quite conveniently are solved now in the second generation of Eurocode 7, or at least guide designers in their design process. These are drainage conditions which shall be used in the calculations, how to deal with pre-existing landslides, weather-related issues and their potential effect on the stability, cyclic and dynamic loading with the whole list of factors which can influence our calculations, and then some other issues, perhaps not directly in clause 4, but I found extremely helpful in Eurocode 7 Part 1, in clause 6, the very detailed guideline how to deal with groundwater levels or pressures is given, because now it was not so clear. And also traffic loads. I'm mentioning it because currently many of us struggled when applying these bridge load models, applying on converting them to the load working on the geotechnical structure. And now in Eurocode 1 Part 2, there is a detailed guidance for simplified models for geotechnical structures, for road and railway load. There is even a possibility of very simple, using very simple equivalent, distributed equivalent load. So very, very convenient. When it comes to verification of limit states, firstly, all potential failure mechanisms shall be verified. There is also a long list of potential limit states to be considered, but actually I do not think there is something new. Obviously, if the level of reliability is not met, we shall consider some stabilizing measures. And also, the stability of existing slopes are now clearly referred to reliability levels in Eurocode EN 1990. Regarding serviceability limit states, there is another list of the considerations, but I think one aspect is really worth of noting. If there is no specific explicit serviceability criteria, the verification of serviceability limit states of slopes may be omitted, provided that ULS is verified. I think it's quite convenient, especially for the designs based on limit equilibrium methods. Another aspect I would like to mention are specific provisions for rock slopes. In the previous session, led by Luis, all those were explained in details, so I just listed here some of these aspects, which are great improvement in Eurocode 7 second generation. However, in the context of our session, I would remind that for rock slopes, the stability may be strongly influenced by discontinuities or other geometrical phenomena. Thus, the partial factors may not cover the situation correctly. So, in that case, we shall apply or reliability-based method can account for these uncertainties and geometrical parameter uncertainties. Another new provision in Eurocode 7 is related to supporting elements. So the retaining walls, anchors, soil ice, rock bolts, and so on. Firstly, the ground structure interaction shall be considered, allowing for the difference in the strength and the stiffness of the ground and the structural element itself. Then, verifying the resistance of supporting element, we shall check the effect of action coming from one of those two formulas. And if you looked in details in these formulas, it means that the effect of action in the supporting element comes from either directly from the design value of ULS calculation or the factored value of representative value coming from the SLS calculation. So it basically means that we shall, as I understood, we shall consider both SLS and ULS in the design, even though the SLS is not required for some cases. It ensures that the supporting element can resist the highest force that could occur during the service life of the structure. Finally, the partial factors. Now we have only one factoring approach for the overall stability, which is the MFA. And when you look into those scary long tables with partial factors, you will figure out that that it's basically what is now DC3. So nothing new. But what is significant? Somebody wants to join us. Horse. You made an entrance. Oh, Ivan. What is significant for all other geotechnical structures, this factoring approach is harmonized. So clause 4 is referenced to regarding the overall stability for all other geotechnical structures. It means that the partial factors I showed here are used in all these other structures design process. What practically means that even if our substructures or structural elements can be solved using different partial factors, when we consider the overall stability, we only verify it using NFA. So I think it's now very, very clear. And also, if you missed yesterday presentation of the report from TGB2, there is a very helpful flow chart for design check of the slopes, cutting and embankments in the TGB2 report. So I hope it will be helpful in this first contact with Eurocode 7 of the second generation. Now, going to soil nail structures, this is a new topic in the Eurocode. And even if they are commonly used for years in Europe, actually there was no design guidance on the European level. We had dozens of different recommendations, guidance, and we have also a very useful execution standard, AM14490 for soil nailing. So basically clause 10 gathers detailed design related aspects, requirements from these documents and fill them with the Eurocode 7 design philosophy. It means that the new clause 10 tries to cover different design practices in Europe and also very different technologies and also extremely different applications of the soil nails, which at the very end of the day means that it was a very challenging task and perhaps you will notice it on some point. Looking into content of clause 10, the subclauses that are worth of special attention are materials, geotechnical analysis, ultimate limit states, and testing. And I will focus on them. The main text is supplemented with informative Annex G with very clear guidance on verification of pull-out resistance for soil nails. Before we go into details, I would remind what is part of the design philosophy in Eurocode 7. Clause 10 obviously describes soil nail structures. However, it focuses more on the soil nails itself, the facing systems itself, about their limit states, material verification, and so on. But regarding the loads working in those elements, the general aspects like ground investigation, these are all covered or referenced in a clause 4, 5, or 7, depending on where we apply those soil nails and facing. And obviously, as soil nail structures often rely on groundwater control measures, we have now new clause 13 dealing with these design aspects. And what's very important, the whole design process includes not only other parts of Eurocode 7, but also other structural elements and execution standards, material standards, testing standards. They are all referenced very clearly in the text, and it may seem difficult, but it ensures the harmonization of the requirements and at the very end of the day the reliability of the structure on the European level. Again, we start with the basics. So soil nail structure are cuttings, slopes, existing structures reinforced with soil nails, which are installed in the ground. So I will notice three things. They are installed in the ground. It means not only soil, but also rock mass fill. There is no limitation regarding the material or the technique the soil nails are installed, and the same for facing. The facing systems covered in clause 10 are sprayed concrete, wire mesh, or other facing elements, including geosynthetics. The general limit states of soil nail structures are, as I already mentioned, to be analyzed according to these basic clauses 4, 5, or 7, considering the beneficial effect of the soil nails. And as I mentioned, clause 10 focuses on limit states of the structural elements itself, which are a rupture of the soil nail, a failure at the interface between the ground and the soil nail, so basically the pull-out, the structural failure of any facing element, the failure of the connection between the nail and the facing, and so on and so on. The list is longer. You can check it in details in the text itself. Regarding the serviceability limit states, some of those specific for soil nail structures are the formation of the facing, the formation affecting the function or appearance of the structure or causing damage to existing structures in the zone of the influence. What is important, here we also have this permission to omit SLS verification if only the ultimate limit states is verified. So it's consequent to what I said regarding slopes in clause 4. When it comes to verification methods for soil nail structure, all of them are also allowed, but we have to be mindful that all these methods have their limitations, have the specific conditions under which they can be used. This is defined in Eurocode 7 part 1. The stability should be verified using limit equilibrium methods and or numerical models. These aspects are covered, as I said previously, in Annex A and Clause 4. And there are no guidance or very dedicated methods for soil nail structures. So we rely on the general provisions regarding the stability. The selected method shall adequately address all potential limit states, but what I think is important point we discussed a lot and finish having this provision in clause 10 is that the verification may be performed using only one design method, as long as it adequately addresses all relevant limit states. I believe it's very beneficial, especially when we are talking about using numerical numerical methods. Regarding calculation of facing or the soil nail and facing interaction, there is a reference to the existing guidance, for example, FHWA manual or BS 806 part 2. In the limit states verification, obviously, for soil nails, we have to check the design effect of action, which comes from this check of according to rules for supporting elements against the pull-out resistance or the structural resistance of the soil nails. And if it's about a pull-out resistance determination, the methods are now somehow harmonized with other supporting elements working in tension, which means that they can be determined by testing, so similarly to how it's done for anchors, or bar calculation using either model pi method or a ground model method, including using comparable experience, which is very popular, I think. But what we should remember, these different verification methods are connected with different model factors, which accounts for uncertainties of the used method, and its value ranges from 1 to 1.6, and also additional requirements are given regarding the testing. And for example, for GC3, Geotechnical Category 3, the pull-out resistance shall be determined from investigation test and verified by suitability test, which basically means that we cannot design them based solely on calculations. For example, using comparable experience, we have to test them. Then, going to the structural resistance of the steel element in the soil nail, it should be verified using Eurocode 3 part 5 or part 1 if we talk about shear resistance as well, or combined shear bending stress. And in all cases, the anticipated loss of strength with time have to be considered. And here we can notice that the issue of durability is highlighted in the text. Consequently, the requirements for steel grade or corrosion protection measures are follow the rules in Eurocode 3 part 5, which basically is in line with what we currently use according to EN 14490. And the last thing is connection between soil nails and the facing. It is to be determined according to the corresponding Eurocode, the structural Eurocode. Then the facing. For the steel wire mesh, there are detailed formulas for determining the tensile and puncture resistance. Again, they consider rules regarding durability and damages, similarly to how it's done for soil nails. And I believe those provisions are the first approach to harmonize such different materials in one document on European level. For other types of facing, their structural resistance should be determined according to the proper Eurocode part. And at the very end, partial factors. When we look into this big table with partial factors, we can notice this philosophy of design. So for general limit states, please calculate it or check it according to the related clause, to the related structure we use soil nails in. Regarding the structural resistance of structural elements in soil nail structure, please go use another structural Eurocode. And for the soil nails and facing, there are two. We can use either material factor approach or resistance factor approach. I added here the specific values to make it easier to follow. And perhaps you can see that it also justifies why we use pull-out resistance partial factor of value 1.25, the same as for cohesion and friction angle in ground. And I would notice also the rules from part 1 of Eurocode 7, which allows us to use the reduction factor when we work in the transient design situation. So it allows us to make those partial factors smaller. But by default, the values are 1. And the last thing, testing. Again, Eurocode 7 part 3 unifies the definitions of the testing for tension supporting elements. And the load testing used for design process shall follow rules of EN ISO 22477 part 6, which is currently being developed. There are 3 types of tests: investigation test, suitability test, and acceptance test. And as I mentioned, for GC3-2, the investigation test and suitability test are mandatory. For other geotechnical categories, they are only recommended. The numbers of tests and acceptance criteria again follows what we have currently in EN 14490. But they are obviously the national determined parameters, so can be changed. To summarize, the provisions for clause 4, slopes, cutting and embankments from the first generation of Eurocode are improved, but no revolutionary changes were made. The overall stability analysis is now harmonized for different geotechnical structures in the whole Eurocode, and the stability aspects of stability in rock were added. Regarding clause 10, obviously, having soil structures covered is a great improvement in Eurocode 7. It collects and harmonizes aspects of design, including material durability aspect and testing and execution. And my personal opinion is that the methods of designing and verifying slopes and soil structures are based on the procedures we currently use in Europe. They do not make any drastic changes. However, we will notice, as I said it on several occasions today, there are no specific guidance. I know it may be, some of us want to have a very specific design path, but I believe that having such an open clause would allow us, at least at that stage, to quite easily fit our national practice and our designers' experience into this very stable framework, which is Eurocode 7 Part 3. Thank you very much. I added also an extra slide with some extra information. I believe it will be distributed after the seminar. I would like also to use this moment to say thank you to all our TGD3, TGD1 and TGD2 members who made a great effort to develop clauses 4, 5 and 11. If you have any question, because we are running out of time, please hold on to them to the discussion part. Now we move on to Stefan Kamp, who will be speaking on example of soil nail from TGB1. Stefan is a geotechnical consultant and team leader in Fugro, in the Netherlands. He has 8 years of experience in various geotechnical projects, and he has been involved in Eurocode 7 works in TGB1 as the young engineer and the new generation. Please, Stefan, the floor is yours.
Good morning. Thank you for the introduction. That means I can skip this part of the presentation and make some time up for the coffee break and the great entrance during your presentation. My case was indeed about slope stability, and as you can see here, it's of course an important geotechnical structure. A lot of geotechnical aspects come into play in slope stability analysis, such as external loads, strength properties, and the groundwater control. But sometimes, to me, it feels like slope stability is not the most favorite subject among geotechnical engineers. It seems a bit dull. It's only soil, no solid structures. So it seems like a bit of a, well, not the best kid of the class. It seems like it. Okay, that's good. That's good to hear. So for the TGB1, we did a case on soft soil in the Netherlands. It's in the Flevoland polder, and it's characterized by the soft soil conditions, a lot of clay and peat. As can be seen here, for the top 8 to 10 meters, it consists of clay and peat, followed by the denser sand layer. The project involved a widening up to 50 meters and up to 7 meter elevation, including additional overheight for the preloading. And that's where the sand fill was used to widen the construction. Overheight was used to accelerate the consolidation process together with the wick drains that were used. And applying this widening and descent fills exactly where the slope stability analysis comes into play on these soft soils, because with every step or every meter that was heightened, the weight of this sand is directly transferred to the pore pressures in the soft soils, and in turn decreasing the strength of the soil. So with every step of heightening the surface level, slope stability analysis must be performed to make sure during the entire construction process stability is guaranteed. So with the second generation code in hand, we assessed this case study. So for the content of this presentation, first the soil investigation and geotechnical category that this structure is in, the approach, some of the analysis performed, and the conclusions in the end. Some of the things have been said already in the first part of this presentation. It's of the slopes and embankments is of course covered in part in class 4. And one of the first steps in the project is to determine the geotechnical category. There's a better focus or more information on getting to the geotechnical category, where it was a bit vague sometimes now. So there are 2 steps before coming to the geotechnical category. First is determining the geotechnical complexity class, and the what applies for class 3 is written there. Considerable uncertainty, highly variable, difficult ground conditions, sensitive to groundwater, and complexity of ground structure interaction. Well, that was definitely the case here. Soft soils, quite variable as well, and as I was sitting here, I thought of the fact that the Almere, the municipality, even has its own additional rules for performing soil investigation for piled foundations. So, well, we can say it's the conditions are complex. Then the consequence class is for a major road of embankment, so that was easy. Consequence class 3, that's mentioned as that in the table. So together that comes to geotechnical category 3, which tells you something about the amount and type of soil investigation, the amount and level of detail of reporting, the type of analysis or testing, as was shown previous. I stole this picture, I must say. So first, after the geotechnical category is determined, we come, of course, to the soil investigation. This was mentioned by Natalia as well. So for this project, a lot of CPTs were performed along the infrastructure until around -20 for the stability and settlement assessments that is considered deep enough, considering the zone of influence, or the most important part are the soft soils. Mechanical boreholes also to collect soil samples for laboratory testing, which consists of classification tests, volumetric weight, water content, pocket tor vein for unweighted shear strength, odometer test for the settlement parameters, and of course triaxial test for the strength. Then more specific, along the highway, which was multiple kilometers, CPTs were performed around 25 to 50 meters, which is quite a normal distance, or center to center distance for infrastructure in the Netherlands. Boreholes every 100 meters. So here you can see a part of the highway and the widening again. I think most importantly, to capture the zone of influence, not only the left part just at the bottom of the slope are important to know, but more importantly at the right side of the slope, which because that part hasn't been preloaded before, most of the soft soils, so for settlement and stability assessments, that's the most important part. well, he said that there's a lot of soil investigation was performed to be able to make a proper design. Well, all of us become more comfortable when seeing some parameters to get a bit of feeling. These were characteristic strength parameters determined for the project based on the lab test and CPTs. I haven't done anything with this assessment because we're determined statistically based on the laboratory tests. Very low unit weights, of course, for the peat, but also very low friction angles for the peat, 15 up to 27.5 for the sandy clay, and low cohesion, of course. Then what's also mentioned multiple times these days, I guess, harmonization of the design for overall slope stability. Now it's the material factoring approach, but this was already the case for the Netherlands, so there's not much change for us. For other structures, it's referred to class 4. You won't forget that anymore. And for the analysis that has been performed for this work group, I think it's good to know that parts of factors can be changed in the end for the National Annex. So I compared it with the Dutch practice, the NEN 997 part 1, and with the parts of factors for the second generation. I will come to the results later. Also, in the second generation, there's more focus on the groundwater, which of course is an important aspect for slope stability, as it directly affects the effective or the strength parameters. In this case, well, the groundwater was monitored in the standpipe for a long period of time, but in this case, in this area, it was also controlled by the water board. So in these calculations, a water level of -5 was used, which can be seen as the nominal value then. Not only the design was part of the comparison, also ease of use and methodology. As I said, not much has changed for the Dutch practice, as it's still the material factoring approach. For the analysis, I didn't check any serviceability limit states. Settlement parameters were not changed and are quite specific for the Netherlands. So it was only about the ultimate limit states, the loss of overall stability, and this is mentioned in the Eurocode of ground test structures in the zone of influence. In the calculation, also a traffic load of 20 kPa along the width of the existing highway is used, as the highway is still in use during widening and construction of the highway, but it was also mentioned more advanced methods or also simplified version is now used or added in the new Eurocode. As it considered many cross-sections that had to be analyzed, a relatively easy method was used, Bishop, but I believe for this use it's a proper method to use. I will come back on the next slide on the drain analysis, and of course for more complex situations, or if it's on the edge of being stable, more advanced methods can be used, such as numerical methods. I think this is the most important part in the analysis for slope stability for infrastructure in the Netherlands. Almost always preloading with sand is used to meet settlements requirements in the Netherlands, which are often 5, 10 or 20 centimeters during a operational lifetime of the highway of 20 years. So those settlements requirements are quite strict. just a couple of slides, almost there. So that's why the overheight is used, and as can be seen in the picture here, every time a meter of sand is applied, also you can see that directly in the access pore pressures. If your structure or your slope is unstable, add some weeks of waiting time, and you're good to go, or adjust drainage measures, for example. Then the results, as expected, no big differences, but for my case, it was for the second generation in CC3, but the original design was in RC2, which was, well, it's 0.99, which is, I think, not stable, but this is just one of the cross sections. And this is, I believe, also a matter of partial factors for that will be nationally determined. So this is one of the difficult parts in this TGB1. You're comparing the national practice with some partial factors from Europe. Concluding, although you have to check all parts and reference are made often, I think it's of course suitable for slope stability, especially in the Netherlands. No new immense changes. Harmonize the calculation methods, and what's also, in my opinion, a good improvement is the more specific guidelines on the guidelines to come to the geotechnical category. Thank you.